What if you could ship a serious LangGraph application in production without ever sending a single token to a hosted provider? That is exactly what we are going to walk through today. LangGraph is the orchestration layer that most tutorials assume runs against the cloud, but the same primitives, state graphs, reducers, conditional edges, structured output work equally well against a model running on your own hardware. By the end of this video, you will understand how to wire a local language model into LangGraph when subgraphs are worth the extra layer, why reducer-based state beats mutating shared objects, and how to add a human in the loop without rewriting your control flow. We will look at real architecture decisions, the kind you would make when shipping a production tool, not toy examples. Almost every long-running orchestration starts the same way. You write a top-level function that calls each stage in order. Then a real requirement arrives. You need to skip a stage when a flag is off. You need to retry one specific step on a transient error. You need a human review gate before the publish step. Each of those changes adds another branch to the orchestrator. Within a few months, your top-level function is the largest file in the codebase. Every helper has snuck in its own conditional, and nobody can answer the question, what actually runs when I press the build button? The shape of your pipeline has become invisible. LangGraph fixes that by making the topology explicit. The orchestrator is no longer a function. It is a graph object that you can inspect, render, and reason about. A state graph is built from two ingredients. Nodes are functions that take the current state and return a partial update. Edges connect nodes in order. You add the start sentinel as the entry point, the end sentinel as the exit, and any number of named nodes in between. The compile step gives you back a runnable graph. Crucially, that graph is data. You can ask it for its node list, render it as a diagram, run it through a doctor command that confirms every edge points somewhere valid. Compare that to an imperative pipeline where the only way to know what runs is to read every line. The shape is now first class. When a new engineer joins your project, they can ask the graph itself what it does, instead of grepping through 6 layers of function calls. Once your graph crosses about 8 or 10 nodes, you start wanting to group related work. A common trap is to flatten everything at the top level, which makes the parent diagram unreadable. The clean answer is a subgraph. You build an interstate graph that owns its own nodes and edges, compile it, and add the compiled subgraph as a single node in the parent. From the parent's perspective, voice is one box. Inside the box, you have the per phase decomposition. Synthesize, process, verify. The state object passes straight through, so you do not need to invent a parameter passing convention. And because subgraphs share the parent state schema, you can move nodes in or out of a subgraph without touching the rest of the topology. That is the kind of refactor that simply was not safe in the imperative version. The most subtle LangGraph idea is the reducer. By default, each node returns a partial dict, and LangGraph merges it into the running state by overwriting matching keys. That works for scalars and dicts you want to replace. But for lists where every node contributes something, warnings, retry events, repair logs, overwriting because the next node would lose what came before. The fix is to annotate the field with a reducer function. Operator.add for lists means LangGraph concatenates instead of over. Now any node anywhere in the graph can yield one entry, and the final state contains every entry from every node in order. You stop thinking about state as a thing you mutate. You start thinking about it as a stream of deltas the graph composes for you. That mental shift alone will clean up most of your old orchestrator code. Real pipelines are not straight lines. You skip rendering when the user only wanted audio. You go straight to a publish step when they passed a republish flag. You loop back when an ASR check flags failures. In imperative code, all of that lives inside the orchestrator as a swarm of conditionals. In LangGraph, you write a small router function, register it as a conditional edge, and provide a mapping from the router's return values to actual node names. The branching is now part of the graph. When you render the diagram, you see every possible path. When you read the doctor output, every routing decision is named, and because the router is a plain Python function, you can unit test it with a fake state dict and a one-line assertion. There is no hidden control flow anywhere in the system. Here is the local first move. The cloud chat models like ChatAnthropic and ChatOpenAI are both subclasses of BaseChatModel. That class is a contract. Implement an _generate method that takes a to list of typed messages and returns a chat result, and you have a fully compliant LangChain chat model. Want to call a local CLI tool? Subclass BaseChatModel. Shell out to the binary, wrap the response in an A message, return a chat result. Want to call Olama? Same shape. Want to use a Hugging Face pipeline directly? Same shape. The rest of LangGraph does not care which model produced the response. Once your wrapper conforms to the BaseChatModel interface, every LangChain combinator, structured output, fallbacks, streaming, works against your local model with no further changes. That is the unlock that makes local first practical. LCEL is the LangChain expression language. The pipe operator composes any two runnables into a single chain. A prompt template is a runnable. A chat model is a runnable. The structured output wrapper is a runnable. So a typical chain reads like a sentence. Take the prompt, send it to the model, parse the output as a typed schema. The result is not a free-form string, but an instance of the schema you specified. Pydantic validation. If the model returns something that does not parse, LCEL raises before your downstream code touches it. And because every runnable shares the same interface, you can swap a cloud model for a local one anywhere in the chain by changing one line. That is why local first does not mean rewriting your prompts. It means swapping a single import. This is the part that makes LangChain feel like a framework instead of a library. Every runnable can be decorated with cross-cutting behavior. Calling with retry on a chain wraps it in an exponential back-off retry loop, configurable for which exceptions count as transient. Calling with fallbacks gives you a primary chain and a list of backup chains. If the primary raises, LangChain transparently tries the next one. Calling with structured output forces the model into a function calling response shaped like your Pydantic schema. You stack these the way you would stack middleware in a web framework, except they compose at the runnable level, so they apply to local models and cloud models alike. The combination is a lot of resilience for very little code, and you do not have to invent any of it yourself. The killer feature for shipping LangGraph in a CLI is the checkpointer. Compile your graph with a checkpointer attached and an interrupt before list, and the run will pause before any node in that list. The full state is saved against the thread ID you passed in. The user can now inspect everything: the generated transcripts, the suggested visuals, the metadata draft. When they are happy, they re-invoke the same compiled graph with the same thread ID and a none payload, and the graph picks up exactly where it left off. There is no separate mode for resume. There is no special second binary. The same code that ran the first half runs the second half, because LangGraph treats the pause as a first-class part of the topology. That is why a review gate becomes one line of config instead of an entire orchestration rewrite. The shape of a healthy LangGraph CLI is a thin command on top of a fat graph. The command function does three things, and only three things. It parses arguments into an initial state, it invokes the compiled graph, and it formats the result for the terminal. Crucially, the command never decides which stages run. It never has an if block on the render flag, because the render flag becomes part of the state and a router inside the graph reads it. It never wraps a node in a try except because retries are part of the graph's compile time configuration. When you keep the CLI thin, every architectural decision lives in one place. The graph defines new flags become new state fields. New behaviors become new nodes. The command function stays the same length forever, and your team's pull request reviews stay focused on the graph diff, which is where the real complexity lives. 3 takeaways to remember. The first one, LangGraph runs beautifully against models on your own hardware. A small custom subclass of BaseChatModel is enough to run any LCEL chain or graph node against a local backend. The second one, treat the graph definition as the canonical orchestration source. Anything important about your pipeline should be visible from the topology alone. New contributors should read the graph before they read any node. The third one, the reducer pattern and the conditional edge pattern all earn their keep in real systems with branching, retries, and human review steps. They feel like ceremony on a tiny example. They feel like a relief on a project with a dozen stages and a dozen feature flags. Pick a workload you are about to write the imperative version of